A container has the shape of an open right circular cone, as shown in the figure below. The height of the container is 10 centimeters and the diameter of the opening is 10 centimeters. Water in the container is evaporating so that its depth h is changing at a constant rate of -3/10 centimeters per hour. The volume of a cone of height h and radius r is given by V equals 1/3 pi r squared h. Part A. Find the volume V of water in the container when h equals 5 centimeters. Include units of measure. The equation that they gave us in the previous slide said that the volume of a right circular cylinder is 1/3 pi r squared h. We are trying to solve for volume, and we know that h equals 5, but we don't know what r is. So how do you find the radius of a cone that they don't even give you the diameter for? You have to look at the proportions of the cone. The one that they had says that the height and the diameter are equal. This shows that there's a 1-to-1 ratio between the height and the diameter at any point in the cone. So, when h equals 5, the diameter also equals 5. This makes the radius equal 2.5. Once you have that, you plug it back into the equation and you solve. 1/3 pi 2.5 squared times 5. You solve that and you get 125 pi over 12. And don't forget the units of measure, and in this case, it is centimeters cubed. Part B. Find the rate of change of the volume of the water in the container with respect to time when h equals 5 centimeters. Indicate units of measure. In the previous slide, we said that the volume is equal to 1/3 pi r squared h. We have the following variables. H equals 5. Radius equals 2.5. The rate of change of the height is -3/10. But we don't have the rate of change of the radius. So we have to find some way to manipulate the volume equation so that we don't need the rate of change of the radius. As we said in the last slide as well, we found that the height equals the diameter. And since diameter equals twice the radius, we can substitute that in and find that h equals 2r. So when you solve it for the radius, you get radius equals h over 2. You can now use this to substitute into the volume equation. You get V equals 1/3 pi h over 2 squared h. Now we're going to simplify a little bit before we put in the rest of our variables. Now that we have this, we can take the derivative of it and be able to solve for the rate of change of the volume. Now that we have it simplified, you can plug in what variables you have and solve. When you solve the equation, you get the rate of change of the volume being -15/8. And the question also specified to indicate the units of measure. In this case, it is centimeters cubed per hour. Part C. Show that the rate of change in the volume of water in the container due to evaporation is directly proportional to the exposed surface area of the water. What is the constant of proportionality? To solve this, we need to have a relationship between the area of the exposed water, which is going to be pi r squared, and the rate of change of the volume. The rate of change of the volume is going to be (1/12 pi 3h squared dh dt, and that's simplified from the previous question. You can simplify it a little farther and plug in the derivative of the height, and you get 1/4, you get -3/40 pi h squared. Now, because this equation has radius and this one has height, you need to somehow make an adjustment to be able to make a relationship. So, we know that from the previous relationship that the height is equal to twice the radius. So in this equation, we are going to plug that in and solve from there, so that we can have common variables. So you continue to simplify this, and you get -3/10 pi r squared. And as you can see, this shows the relationship because you now have pi r squared in the equation. So, the rate of change of the volume is equal to -3/10 times the area of the exposed water. This gives you that the constant of proportionality is -3/10.